Hey everyone. So let's talk about segment routing in massively scalable data center. I have a packed agenda here, so let's start straight away. Okay, so this is briefly what I have. So I'll just talk a little bit about BGP and MSDC. Most of you already know a lot about it. Peter mentioned it in his presentation as well. A little bit about the DC architecture evolution, and essentially then we talk about a few problems which we see today, which can be solved using the segment routing solution. And then we talk about a little bit about segment routing in general, the BGP version of it, and a couple of use cases which are specific to the MPLS data plane and the IPv6 data plane. And let's start. So the base prerequisite for the segment routing in data center proposal in this presentation is use of BGP in a massive scale data center. So a lot have been talked about it, and many massive scale data centers today are using BGP, mostly BGP. And it came, the key takeaway from this slide is basically how it came to a data center, the BGP, is because of the rise of virtual machines, the virtual machine migrations, big data, and essentially application-driven traffic, increase of application-driven traffic in the data center, and a lot of east-west, the inter-server communication, vis-a-vis the classic north-south, which used to come and go in the TORs and the DCIs. So again, I mean, this outlines a little bit about why BGP is a very suitable protocol for in a massive scale data center. So of course, it's well known, it's simple, it's comparatively quiet once you establish. We have inbuilt loop detections and also autonomous system which can differentiate domains pretty easily. ECMP is available, and we have recursive next hop resolution already inbuilt. There are some issues typically stems out from the possibly slow convergence at times, but we can use techniques like BFD to compensate for some extent. So this is the evolution most of us already seen in data centers, how the classic, the edge aggregation core became the clause. Here's a folding clause in this slide, but yeah, you can fold and fold it as you like. Key thing is, again, like this came into being because this is very suitable. This architecture is very suitable for the east-west traffic. And it's easily scalable. Either scale up with a higher port density at any level, or you can add more levels as needed, which is basically scaling out or horizontally. So now marrying the two ideas, BGP in MSDC and a clause model. So now we have a kind of a reference diagram for my whole presentation is this. I kept it very similar to the diagrams which you will see in the related drafts as well, so that you can read it later and then kind of picture this in mind and then correlate the two. So as you can see, like we are basically proposing all the spine nodes would be in a single AS, and the cluster of the leaves will be in the same AS also, and each of the TORs in the separate AS. Yeah, this is. You can actually do it also in IBGP if you really want. You can do it like you need a route reflector at each level, and also you have to do a next hop self and then all that. But yeah, you can do it in IBGP as well, but the preferred method is eBGP. And yeah, I mean, needless to say, you are always getting an ECMP fan out as you go from one side up to the other, east-west. So now that we establish a reference diagram, reference topology for our presentation. Now we go about talking a few key problems which you are thinking of solving using segment routing solution. So first one is the part flow versus part flow rate. I'm pretty sure many folks already have discussed this among yourself in your company. So essentially, part flow means we always have a view of end-to-end. So flows are source to dest. So if you do not know the exact path being traversed between the source and destination, there are many granular calculations, monitoring, and all other stuff you cannot do just because you don't have the idea of exactly which path is being taken from source to destination. So that gives rise to what I call a elephant and mouse flows problem. I have a separate slide to describe that. Then, of course, the same problem gives birth to another a more generic issue, which is the performance unaware network imbalance oblivious ECMP. So something happens in some part of the network, and since you do not have enough granularity to know how exactly your data packets are being routed end to end, so you do something on one end, mostly in the source, which is not really taking care of that fault or that issue, which you have somewhere else in between your data center. So that we can resolve with this. We'll see that as well. And then third one is basically the generic problem statement. You have a very a black box view of the network if you know only about the source and the destination. But we want to know more granular, more details about the exact path which we want to traverse from source to destination. So we want a white box view of the network. And then, of course, that also enables you to do a deterministic network probing. I think Peter's presentation also talked about how we can send end-to-end pings and then get them back and then see and monitor and detect faults or even see performance degradation in certain areas of the data center. So we can do all that if we have a further granularity. So this is a little bit about the elephant versus mice flows. Elephant flows are essentially the very large size, very, very long-lived, and huge data transfers. That's a typical example. And they're very throughput sensitive. They don't care much about latency as obvious. Database cloning, backing up stored data from one place to another, and of course the VM migration, which we talked about earlier. These are typical examples of elephants. Whereas mices are essentially, they're much smaller size, short-lived, and they're typically bursty, and of course they are latency sensitive rather than throughput. And this is like your regular web browsings, emails, social media posts, and so on and so forth. Now, in the data center, most of the flows are mice, of course, as evident, but majority of the bytes or the packets belong to the very few elephants. So now, what happens is if you have only an end-to-end view and not the granularity of the network, so you end up hashing many of the end-to-end flows to the same path. Like in this example, you can see that the two elephant flows, blue and yellow, they're going via a path because of the hashing. And mice flows, which have the same source and destination, will more likely than not will be put on the same path. So those elephant flows will, first of all, we do have paths for two elephants in two different, there are paths available. Like for example, look at node 3. You have that black path via node 6 and node 9 to go eventually to node 11, but you are not taking that because you don't know the, the granularity of that, the availability of that path in between. Whereas, so both of them going via the same path, eating up the resources, and the mouse, when the mouse flow comes, he sees the network buffers have already been eaten by the elephants. So the key thing for the mice flows, which is latency, is being compromised. So this is something which we see a lot in today's data centers, and of course, as and when we see more advent of this kind of technologies like virtual machines and big data, it will be more and more evident. And this is if you remember the second part of the problem, we talked about the network imbalance oblivious or performance oblivious ECMP. So see, in this scenario, what happens, node 3, there's a fault in between node 5 and node 9, which is a leaf and a spine. So there's a fault there, there's a performance degradation there, but node 1 has no idea about it. So it keeps on sending load balance traffic to both 3 and 4, even though 4 is able to take away the whole traffic, 3 is only doing the half of the job. So essentially, it should have sent 1/3 to the node 3 ideally. But it's sending roughly the same amount of traffic to both 3 and 4 because it does not have any idea that there's a fault between 5 and 9. And it sees there are alternate paths available from 3. So what's the solution? So the proposed solution here is the segment routing. I think many speakers before in earlier NANOGs and other such communities have talked about segment routing a lot. So Essentially, it's called source packet routing in networking, SPRING in short. So it enforces the flow through a certain path. So essentially, it gives the granularity to the flow which we want. We just don't say, okay, this is the source, send you to the destination. Rather, we send, okay, go, this is the source, go via these exact nodes or exact links to that destination. So part flow state remains only at the ingress node. We don't keep in all the nodes in between, unlike some protocols like RSVPT does. And of course, that comes down to the third fact, which is the no need of a separate MPLS control plane like LDP or SVP. And it definitely allows incremental deployment. If some of your nodes in your network does not support, is not possible to support segment routing, it's perfectly fine. You still can achieve some of the benefits of segment routing. And it does it's applicable seamlessly to MPLS as well as the IPv6 data planes. We'll see that in the other slides. A few definitions. I'm sure most of us are already aware of these. A segment is basically an instruction. Like if you apply to it an MPLS data plane, it will be mostly popping, pushing, swapping a level. And if you do it in IPv6, it's very similar. It just decrements a header, which is an extension proposed by the segment routing draft, and modify the destination address accordingly. So segment identifier in MPLS data plane is nothing but an MPLS level. IPv6 is an IPv6 address. Segment list, of course. So since we are talking about source routing here, it sends a stacked list of segments. Like in case of MPLS data plane, it will be a stack of MPLS levels, or IPv6, it's an IPv6 address list. And that's called a segment list, which is available in the source, and it sends the traffic with that list. And the segments can be global and locally relevant. Some of the segments basically which you want to identify a certain node in your data center uniquely. So those will be a global segment identifier. And some of them are relevant only in a node locally. So for example, you want to give a certain traffic to a certain service in a node, and no other node needs to know about it other than that node. So those segment identifiers are basically locally relevant. We talk a little bit more about them in the next slide. So this is the two types. The first one is basically the global prefix seed. So this is essentially a segment attached to a certain prefix. There are two variants. We'll talk more about the first one, which is the node segment identifier, which identifies a specific router, typically the loopback address or the router ID. The other one is Anycast. Again, I'm lucky to have Nick talking a little bit about it today morning itself. So Anycast seed, which identifies a set of routers, of course, and it's attached to the Anycast IP rather than the router ID. And then similarly, there is the local adjacency seed, which is local to a certain node, and it identifies the information which is only needed or available locally, like a service in that node, or a certain link in that node, or a pair of links, or an adjacency in that node, or an interface, something like that. So this is the very familiar picture of the segment routing. I think many presentations everywhere in the web has this. So essentially, I'm sending a packet from node 61 to node 66. And I want to take a path to node 65. And then I want it to go to node 64, not the ECMP, the IGP ECMP path of 65 directly linked to 66, but to 64 first and then to 66. So we just push the segment identifier accordingly. Like in 61, I first put the segment identifier for 66 at the end because that's the end destination. Then 9001, which is relevant only for the node 65 to take the traffic towards node 64, and then towards node 65. So the traffic is ECMP to 61 to 65, and then 65 it looks at the 9001, which is locally relevant, and sends it towards the link, which is 6564 link, which is identified by the segment identifier 9001, and then it goes to node 66 eventually. So essentially the takeaway again is that we are defining the exact path which this data traffic need to traverse. So this is the BGP variant of it. This is the draft which talks all about it. So this is essentially the same thing which we talked about, but now it's specific to BGP. It's advertised by BGP. When we talked about global local scopes, this time it's a BGP domain or the autonomous system. The ECMPR shortest path is the shortest path computed by BGP in this case. And we will be primarily using the first variant, the node seed or prefix seed, which is identifying a router or a node uniquely in the data center. And it can be, of course, represented either as a label, which is an MPLS data plane, or an IPv6 address, as we said already. So these are the protocol extensions which you need for having BGP segment routing. So if you are using it with MPLS data plane, there are a couple of TLVs proposed. One is the label index, which is advertised by the originating node, and it remains the same throughout. And there will be an optional segment routing global block. You use these two values to calculate the label, essentially, which should be attached to that prefix. And then here's the example of the incremental deployment I was talking about earlier. If you, some of your nodes does not support this, they can simply use the regular BGP 3107, which is a labeled unicast, and you will still be able to carry on the traffic as you did already. So the same story in the IPv6 side, which is has an IPv6 segment identifier TLV. And since we don't have a kind of stacking mechanism which we have in MPLS, so there is an extension proposed which is called a segment routing header for IPv6. We'll see that shortly. So again, coming back to that old picture which we had already in our presentation. So each TOR in its own AS, leaf nodes in the same cluster in the same AS, and all the spines in the same. And we are using eBGP labeled unicast in this case, since we are using MPLS data plane. It's hop by hop everywhere. And of course, as I told earlier, you can use iBGP as well, but preferred method is with eBGP. So this is a very busy slide. I won't go all the way to the details. It's you can read at your leisure later. But the idea is Node 11. It's an example of flow between the A and Z, which it can be servers or applications running on the servers. And basically Node 11, when it's advertising with an index 11 of its own node seed. And this index 11 remains the same throughout the path, which I have identified using the dotted lines. So when it eventually reaches the node 1, through all the ECMP paths available, you know the exact path need to traverse for reaching eventually to Z via node 11. So again, the idea is the granularity which we want between the source and the destination, and it's evident how clear it is to the source node now. And of course, the label can be stacked in the ingress to steer the traffic, including or excluding the nodes as you like. So it's pretty similar in the IPv6 use case as well, but since, yeah, of course, we talked about the problem that we don't have really idea of a stacking of IPv6 addresses. So in this case, we have an extension proposed by the draft mentioned here, which is basically called a segment routing header. So just like an MPLS enabled router would, pop the label which it understands, and then pushes swaps another level to take it to the next destination. In this case, we have a segment routing header, which will be having stacked IPv6 addresses, and actually the next diagram will clear it even further. And whenever it's any of the this SRH enabled nodes see its own prefix seed already mentioned in the header, it just pops it out and then takes the next one in the header stack and put it into the destination address and routes it towards it. So if you see from node 1, it wants to reach node 11 via node 7. So it pushes the 7's address, of course, as destination, and also it pushes the end destination, which is 11 first, and then on top of it, it stacks the 7. When 7 gets it, he sees his own seed here in the segment routing header top. It pops it and then copies the next one, which is 11, in the dest address, and then when node 11 gets it, it sees nothing else is there in the segment routing header, so it must be meant for himself. So it's pretty similar to MPLS data plane in the logic perspective. And now we look back at the problems which we already discussed, and how are we solving with this solution. So there is an addition of a small green rectangle at the top. Of course, that's the controller. And so now if, and the controller is running a BGP link state, which typically with most of the nodes in the data center. So what essentially we are doing is we are learning the path end to end, like how we mentioned already, and then communicating to the controller via the link state. So the controller now have a much more granular view of the whole data center and how to, he knows now all the possible paths to route the packet from one into the other. And he also knows if we keep monitoring those specific paths over time, the performance issues, the possible alternate paths available, and all these details. So now it can push the exact path to the ingress node, and now we can see how we can solve the problems that way. Like now you see the two elephant flows are taking two different paths starting from node 3. It now is aware that the node 1 is now aware that node 3 has two alternate paths, so no need to hog up bandwidth in one and then leave the other one unused. Similarly, we are separating out the mouse flows and elephant flows altogether. We are not routing the mouse flows anymore along with the elephant flows, and we are giving it a low latency path which is still available via the node 4 instead of the node 3, right? And similar case, like now we see there is an issue between node 7 and node 10, which is previously we saw in the imbalance oblivious case, which is the current scenario without SR, is we still try to keep on load balancing from the TOR side. But now that we know there are two distinct paths, right? One is via node 7, another via node 8. We just remove the path via node 7, as you see it's cut, and we just take the path via node 8, and now we can balance our traffic much more accurately. So that also results in dynamic fault avoidance. Anywhere if there is a fault happening in any part of the network, we know in every granular detail about it, and then we can take the corrective actions. So fault isolation, fault detection, and also the fault avoidance can be done much more efficiently in this scenario. A little talk about the controller part. So BGP link state is the basically a new address family which is helping the controller to know the whole topology. And how you push the data of the end-to-end flow to the ingress from the controller is not really inside the scope, but you can use something like PCE, which Alia talked about a little bit. And also we have segment routing traffic engineering being developed as a separate draft, which will help using, doing the same thing using BGP itself. These are the references. The first one is pretty much the one-stop shop for everything segment routing. You can just go there, all the drafts mentioned there. I still mention the key drafts which I use for this presentation mostly. Yeah, of course, I mentioned the RFC for the BGP level unicast as well, which is used in the MPLS data plane. I have a few appendices. I think I have some time to little bit talk about them. So there is an extension. If you remember the slides when we showed about, like, there are two types. Like one is a globally unique SIDs, which are basically our node SIDs or prefix SIDs. And there are something as locally unique or locally relevant SIDs, which are the adjacency SID. So we really didn't talk about them in the BGP solution yet, but we can use them sort of away here. So focus on the PRC, the BGP PRC, which is essentially an egress for its AS1. Now, a node in A or B, we can give a way to choose a path from C rather than the default BGP chosen path, say, which is through D. If we use the adjacency seed, how? Like if we give a certain ID to the adjacencies from C to D or C to E, like in this case 304 and 305, then you can tell A or B exactly which path to take. You go to C first via the node seed of it, and then go either towards D or you go towards E, or you can even have both of them combined to something called a peer set seed. And if you use that for your flow, then you're getting basically a protection mechanism as well, where if say D or the CD link fails, you have another path to go. So this is a very active draft as well, the BGP egress peer engineering, in short, EP, which I mentioned here. So then you have a bunch of protocol extensions. This is primarily needed for the BGP link state, which the controller uses to learn about the network. And it needs the extensions for both the prefix seeds as well as the adjacency seed, the EP seeds which I talked about. Okay, and this is primarily east-west traffic, inter-server traffic, and the problems related to it, and how we solve that with segment routing. But you can easily extend this idea to north-south traffic as well. And essentially, again, we talked about two different types of prefix seeds. One we talked a lot about, which is node seed, of course. But there is that anycast seed, right? And if you use that efficiently, especially in the leaves and spines, you can end up having something which you call color-based architecture, where you can basically use the fully CMP path if you use just the prefix seed itself. But if you use the anycast seed, you can actually mark a few of your leaves and spines to take a certain kind of traffic. So for example, in this case, you can tell, okay, all my elephant flows goes via the orange path, whereas all my mouse flows will go via the green path. So this is applicable equally to east-west as well as the north-south path. And yeah, there are, again, drafts being worked on this solution as well. So that's about it. I'm done. So any questions? Anyone?
Owen DeLong, Akamai. In the case of the IPv6 implementation, you're talking about adding potentially mumble 100 octets of extension headers onto the front of your packet.
Right.
What have you done about the MTU considerations that might imply?
Okay, so yes, I mean, for the IPv6 case, yes. I mean, even for MPLS case, for that matter, if you see, there will always be talks about limits on how many levels you can push on the source. I mean, typically you will, I don't know, I mean, maybe you can push 3, 4, the capability might be of 7, 10 levels at most. So yes, those things will be there, but the key takeaway is that in case of a data center where you really not traversing a whole lot of boxes, first of all, from the source to destination, unlike a service provider kind of a scenario. And secondly, even if you jump a few levels, right, and mention a transit node which is a little farther from the source, you still get the eCMP for free. So while I agree that there will be a limitation due to the MTU and other factors for IPv6 and level pushing for MPLS, you still can achieve a lot of the data center specific advantages of segment routing if you push a list in the source and to make the traffic take a certain path which you like to. Anything else?
Big Victor from Visa. So my question is actually, you answered half of it. So source routing is in the control plane, and segment routing give you something similar to what the label stacking in MPLS.
That's right.
Then why am I taking it if I already have a MPLS to do the data center interconnection there? And how big is your mass scale, data center?
Sure.
Like you mentioned, 4 stacks is already, big enough for the majority of the data center interconnection, right?
Yes. So when talking about the pure source routing, as we know, there are limitations. There are a lot of limitations, right? Like here, what I'm doing essentially is I'm taking the advantage of the logic or the the clarity or the granularity which we get from source routing, but we are using the the scalability factor of BGP and the MPLS data planes or IPv6 data plane when the question of taking the traffic from source to destination is concerned. So kind of assumes that you already have BGP in your data center and you're using it for the scalability factor, and you either have MPLS, the level unicast most likely for the data transfer, but you can have IPv6 as well. But yes, so you already have that infrastructure in place, and then with very minimal changes in the control plane side, you are essentially getting a benefit which is helping you to steer your data in the exact granular path which you want. But you couldn't have achieved that if you use the regular IPv4 source routing. Still have some time. Anyone else? Good. Thank you.